Hello friends, welcome to the class of BSc third year mathematics. In the paper of real analysis part first, up till now we have studied two chapters. The first was sets and functions, and the second chapter we have studied is sequences of real numbers. Now we shall study the third chapter from this paper of real analysis. The third chapter is series of real numbers. So I have written some preliminary definitions here and one first result I have written, and now we shall see what is the meaning of the definitions. So the first article is convergence and divergence of series of real numbers. First we define what is infinite series. Here we have to study infinite series of real numbers. The definition is the infinite series, which is denoted by this notation sigma. Capital sigma stands for summation, and n takes values from 1 to infinity an. Summation is taken over an, n takes values from 1 to infinity. This is the notation for infinite series, and this is an ordered pair. Ordered pair, first these are two sequences. First is an, n takes value from 1 to infinity, and second sequence is Sn, n takes value 1 to infinity, where an is a sequence of real numbers. We have studied sequences earlier and we have denoted the sequence by this notation. We are following the book Methods of Real Analysis by R. Goldberg, and the notation used for sequences is this type of notations, an and Sn, where n takes value from 1 to infinity. That is a sequence of real number, and whose terms will be a1, a2, etc. And the second sequence, the expression is Sn, we have denoted it by Sn, and Sn is a1 plus a2 plus so on up to an. That means sum of first n terms of this series an, sigma an. N belongs to I. The number an is called, in this series, this number an is called nth term of the series, and the number Sn is called nth partial sum of the series. This is a partial sum, sum of first n terms, and because the series is infinite, the terms will be go on adding up to infinity, and thus this Sn is called the nth partial sum of the series. So these are the terms related to infinite series. Actually there will be two sequences, but we have to consider the sequence of partial sum. And this is important because the series, convergence or divergence of the series depends on the sequence of partial sum. And thus for every series, infinite series, we attach a sequence of partial sums with the series. And that is denoted where Sn is denoted by a1 plus a2 summation plus an, sum of first n terms is Sn, and this Sn is called the sequence of nth sequence of partial sum, and Sn is actually called the nth partial sum of the series. Now we define the convergence of the series, convergence or divergence of the series. When the series is said to be convergent and when it is said to be divergent, that is given in this definition. Now see the series, example of a series can be written as a simple series 1 plus 2 plus 3 and so on up to n plus 1 etc. This is a series, and here this the general term of this series is n, so this may be denoted by summation n takes value 1 to infinity, infinite series, and or otherwise we can consider this also as 1 by n. We are going to consider these examples after preliminary definitions, but the meaning of series, the terms can be written in this order. Now what will be the first term of the series? If you take n is equal to 1, we should get the first term, and next plus n is equal to 2 means 1 by 2 and plus 1 by 3 and so on up to general term is 1 by n. But it doesn't stop there, it is infinite series and therefore it continues. The next will be 1 upon n plus 1 and so on. So thus these are the examples of infinite series, and the nth term is here an, that is n. n is the nth term of the first series and 1 by n is the nth term of the second series. Now here we have written the definition of convergence or divergence of series. Let summation an or sigma an be a series of real numbers with partial sums as above we have defined. Partial sum denoted by Sn and meaning is sum of first n terms, that is a1 plus a2 plus up to an. N belongs to I, and from this we can form s1, s2, s3, etc. If this sequence Sn, sequence of partial sum, converges to a some number, real number, a belongs to R means a fixed real number, a belongs to R, we say the series also converges to a. So that is simple meaning of the convergence of infinite series, that depends on the sequence of partial sums. If the sequence of partial sum is convergent, then the series is convergent. Or if the sequence Sn converges to a, then we say the series also converges to a. And second part, when the series is said to be divergent, so this Sn converges, the series also converges. And again, if Sn diverges, then we say the series sigma an also diverges. So that means the behavior of the series depends on the behavior of the sequence of partial sum. If it is convergent, the series is convergent, and if it is divergent, the series is divergent. And what is the partial sum? That is Sn, sum of first n terms of the series. We form a sequence of these partial sums and then decide whether it is convergent or divergent. If it is convergent, the original series or the series sigma of an is convergent, and if Sn is divergent, then sigma an is divergent. So this is the definition for convergence and divergence of the series. And next, if sigma an converges to a, generally we write sum of the series, infinite series, equal to a. That is a notation for denoting the convergent series. If it converges to a, we write sigma an is equal to a. The sequence converges to a, that is also considered as the sum of the series, or sum of the series is equal to a. Now this is our first theorem from this chapter, that is, see, if summation an or sigma an converges to a and sigma bn converges to b, then sigma an plus bn, n takes value 1 to infinity, converges to a plus b. So that is first part. And also if c belongs to R, then sigma c into an converges to ca. Now what is the first part? If there are two series, both convergent, first converges, the two series are denoted by sigma of an and sigma of bn. The first series converges to a, the second series converges to b, then this type of series sigma an plus bn, whose terms will be, first term will be a1 plus b1, second term will be a2 plus b2, etc. And thus this series converges to a plus b. That is first part. And second part, if c is constant, real number, then sigma c times an will converge to c times a. That is the second part. Now we shall prove this theorem. So we have first defined these terms and then stated the theorem 1. Now these results can be proved using the results from sequences, because the convergence of the infinite series depends on the convergence of sequence of partial sum. Now I shall write the proof here. First we shall form the sequence of partial sum of an. Now here we have Sn. Sn is a1 plus a2 up to an, and that we shall consider. Let Sn is equal to a1 plus a2 and up to an, and we shall denote the partial sum of second series sigma of bn by tn. Another notation we shall use. These are notations used for denote first and second series. An and bn are the nth term of first and second series. Now what will be tn? Tn will be sum of first n terms of this second series, and that first term will be b1. Take n is equal to 1, we will get b1, plus the second will be b2, and the nth will be bn. So these are the partial sums of the series sigma an and sigma bn. Be the nth partial sums of the series sigma of an and sigma of bn respectively. Now it is given sigma of an converges to A, means sigma an is equal to A. So given or by hypothesis sigma n takes value 1 to infinity is equal to A, and sigma of bn as n takes value 1 to infinity is equal to B. So what is meaning of this? First series converges to A means what? The series, the nth term, see Sn converges to A for this series. Yeah, Sn is the partial sum of the first series. So therefore Sn converges to A, and what the second means, sigma bn is equal to B means the partial sum of this series, which is Tn, and that must converge to B. This is by definition. So therefore we have limit of Sn as n tends to infinity is equal to A, and limit of Tn as n tends to infinity is equal to B. Now we want to show this series converges to A plus B. So for that purpose we have to write the nth partial sum of this series. Now, and that will be now nth partial sum sigma n takes value 1 to infinity an plus bn is, see, it will be first term a1 plus b1. We run n from 1 to n. So second is a2 plus b2. We should write in bracket, and plus the last is nth, means an plus bn. So this is equal to, now we can group these terms ai's and bi's, and that is a1 plus a2 plus so on up to an plus b1 plus b2 so on up to bn. And what is the first bracket? See, the first bracket is Sn, and that is Sn plus, and the second is Tn. So the nth partial sum of this series is Sn plus Tn, and now we shall find its limit of nth partial sum. And therefore see limit n tends to infinity of Sn plus Tn. Here we shall use the result from sequences, and we have in the chapter of sequences proved that this limit of convergent sequences is equal to limit of first sequence plus limit of second sequence, and that is limit n tends to infinity of Sn plus limit n tends to infinity of Tn. And what is limit of Sn? Here it is A, because first sequence series converges to A, and limit of Tn is B, and thus the limit of Sn plus Tn is equal to A plus B, means the nth partial sum of this series converges to A plus B, and this shows that the series converges to A plus B. So this shows that sigma n taking value 1 to infinity an plus bn converges to A plus B. So this is what we wanted to show. This converges to A plus B, and This proves the first part of the theorem. Second is easy. If C is in R, means C is a constant. Further, if C belongs to R, we have the nth partial sum of this series, sigma C an. Is, so that will be C times A1 plus C times A2 plus so on C times AN, or which is C is common, and that can be written as C into A1 plus A2 up to AN, or this is Sn. See, this is Sn, CSn. So nth partial sum of this series is CSn. And now limit n tends to infinity of CSn. This is also theorem from limit of sequences. C is a constant, and this will be written as C into limit of Sn. And what is limit of Sn? That is here, it is A. So therefore this is equal to C into A. And thus this proves that this series C into An, sigma C into An converges to C into capital A. So this shows that, or this proves that the series summation C into An converges to C, and this proves the theorem. So this is hence the proof of the theorem first. So here we have proved that if two series are convergent, sigma An and Bn are convergent, then sigma An plus Bn also converges to the respective sum A plus B. Now a consequence of this is, for the difference it is also true. Convergent sequences, that we will write as a remark. In the above theorem, in the theorem 1, we also have this result, that is summation n takes value from 1 to infinity. An minus Bn will converge to A minus B. Sigma An plus Bn if converges to A plus B, and if you consider instead of plus sign for addition, subtraction we shall consider, then it will converge to A minus B. So this is the immediate consequence of the theorem. Now we shall consider the second theorem. The theorem number 2 is for convergent series again. If sigma An is convergent series, is a convergent series, then limit of An as n tends to infinity is equal to 0. So this is an important result for convergent series. If summation An is a convergent series, then the limit of its nth term must be necessarily 0. So that we have to prove. Now for this purpose, again we shall form first the partial sum of this series. And that we have already denoted by Sn. So let Sn is equal to, Sn is sum of first n terms, A1 plus A2 plus up to An. And if this is Sn, so we also write therefore what will be Sn minus 1, sum of first n minus 1 terms, and that will be A1 plus A2 plus so on up to the last will be an minus 1. So these are the partial sums, nth partial sum and n minus 1th partial sum of the series. Now this series is convergent. So we shall consider, given this is a convergent series, and we shall assume the series converges to A. So we can write as, since or by hypothesis it is given summation an is convergent, and therefore this sequence of partial sum must also be convergent. And suppose that converges to A. Let sigma of an as n takes value from 1 to infinity is equal to A. Therefore limit of Sn as n tends to infinity is equal to A. That is by definition, if the series converges to A, the sequence of partial sum also converges to A. And if limit of Sn is A, what will be limit of Sn minus 1? That also we shall write. So therefore limit n tends to infinity of Sn minus 1. What will be this? Now you see, as n tends to infinity, Sn minus 1 also becomes larger and larger, or n minus 1 also tends to infinity if as n tends to infinity. And therefore for a convergent sequence, limit of Sn and limit of Sn minus 1 is the same. Or for a convergent sequence, all its subsequences also converges to the same limit. Limit cannot be different. And therefore limit of Sn, if limit of Sn is A, limit of Sn minus 1 is also equal to A. That we should note. And now what we have to show is the limit of An. Now we shall form An in terms of Sn and Sn minus 1. Now An is equal to, now see what is An in terms of this. Here the earlier term is An minus 1, and if we subtract Sn minus 1 from Sn, we will left with last term An. So therefore An is Sn sum of first n terms minus Sn minus 1. It can be verified from this. Difference of these two is the last term An, because the earlier term is An minus 1 and it will be cancelled in subtraction. So An remains in this difference of Sn minus Sn minus 1. Now we take limit on both sides. Therefore limit of An as n tends to infinity will be equal to limit n tends to infinity of Sn minus Sn minus 1. And you see, this is limit by the theorem on limit of sequences. This is limit of Sn minus limit of Sn minus 1. So these theorems we have proved in chapter of sequences. And now, but you see what is limit of Sn? Limit of Sn is A as n tends to infinity, and limit of Sn minus 1 is also equal to A as n tends to infinity, and therefore this is equal to 0, and thus we have proved limit of An is equal to 0, and this proves the theorem. If the sequence if the series is convergent, sigma An is convergent, then limit of its nth term is 0. Now we shall consider a few remarks on this theorem number 2. I shall write here remark for this theorem. Second, first is the converse of this theorem is not true. Converse of theorem 2 is not true. So what is the converse of this theorem? Converse statement of conditional. If sigma, the theorem is if sigma An is convergent series, then limit of An is 0. The converse will be that is limit of an is equal to 0. If limit of an is equal to 0, then sigma an is convergent, that is converse. But it is not true. That is, the meaning is, that is, if limit of an is equal to 0, then sigma an need not be convergent. This need not be convergent. That is the meaning of converse is not true. May be convergent, may not be convergent. And we shall write one example, and that is sufficient to show the converse is not true. For example, the series sigma n takes value 1 to infinity 1 by n is, we shall prove this is divergent. Is divergent, though what is limit of an, or though limit of an, that is limit of nth term, means 1 by n. And what is this limit? This we know limit of 1 by n as n tends to infinity is 0. So thus this is 0, limit of an is 0, but this series is divergent. So this shows that the converse of this theorem is not true. So we should use the theorem in this way only. If it is convergent series, then its limit of nth term is 0. And now we shall consider the second remark. We will take the contrapositive of this statement. The contrapositive of theorem 2. I shall write the second remark here. The contrapositive statement. Or contrapositive is always equivalent. Statement of theorem 2. Theorem 2 is, we know what about a conditional statement. P implies Q, and this is equivalent to negation of Q implies negation of P. These are two equivalent, always true, and therefore contrapositive of this statement is true, and that is true. That is, what is that statement? Negation P implies negation Q. Means negation of this part or negation of this statement implies negation of this statement. Or in other words, if limit of an as n tends to infinity is not equal to 0, then sigma an is not convergent, or that is divergent. So is the contrapositive. So that is, limit n tends to infinity of an is not equal to 0, then summation an as n takes value 1 to infinity is divergent. Not convergent means it is divergent. So this is the result, and we should remember this also. If a limit of nth term, it is a negative test, but it is useful. If we know the limit of nth term of the series is not converging to 0, then we say the sigma an is divergent. So for example of this, we can consider the series. Or the series, say n taking value 1 to infinity, we may consider simple series n plus 1 divided by, say, n plus 3. What is the limit of an? Limit n tends to infinity of an is equal to limit n tends to infinity of nth term of this series is n plus 1 divided by n plus 3. And we know how to obtain the limit of such expression. We divide the numerator and denominator by n, and thus this is equal to limit n tends to infinity. If you divide by n, the numerator will be 1 plus 1 by n. Divide each term by n at numerator, also at denominator, and the denominator is 1 plus 3 by n. And further we know that the limit of 1 by n as n tends to infinity is 0. So therefore this becomes 0, and this is also 3 into 0 means 0. And thus this is 1 plus 0 divided by 1 plus 0. Since limit n tends to infinity of 1 by n is equal to 0. And thus this is equal to 1. So limit of an is 1. And you see limit of an is not equal to 0. Non-zero limit. Then that implies the series is divergent. So this is not equal to 0. Therefore, the series n taking value 1 to infinity, this series is divergent. So thus the theorem 2 is important. From that theorem we can show whether the series is divergent or not by taking the limit of its nth term. Now we shall consider some examples from exercise. Problems from exercise 3.1. So some simple examples we shall consider show that the series summation 1 upon n into n plus 1 as n takes value 1 to infinity is convergent. We will make use of the results that we have studied up till now. Now when we say this series is convergent, if the sequence of, by definition, if the sequence of partial sum is convergent, then this series is convergent, and therefore we shall form the sequence of partial sum. Here this is nth term of the series, and so we can write this as an. Let an, so that will be the nth term of the series. An is 1 upon n into n plus 1. But this can be written as, now you see, we can write this as 1 upon n plus 1 minus 1 upon n, or you should check, this should be 1 upon n. 1 upon n minus 1 upon n plus 1. So this must be like this. You can verify, if you subtract this, n plus 1 minus n, that is 1, and the denominator is product of these two. So this expression is written in this form, equivalent form, or other words, these are partial fractions of this simple term. So we have written directly 1 upon n minus 1 upon n plus 1. The difference is exactly this one. So this is an, and let Sn is, or we now form the partial sum of first n terms, that is a1 plus a2 plus a3 up to an, and therefore this Sn will be, what is a1? From this we will use this expression, so it will be helpful for addition of the terms, and put n is equal to 1, this will be 1 by 1 minus 1 by 2. Next is plus a2, put n is equal to 2, this is 1 by 2 minus 1 by 3, and put n is equal to 3, so this is a 1 by 3 minus 1 by 4, 3 plus 1, and plus so on. The last is as it is, 1 by n minus 1 upon n plus 1. Now what is the sum of this? You see, in the expression we observe that this minus half and plus half becomes 0, minus 1/3 and plus 1/3 becomes 0. Similarly, minus 1 by 4 and next plus 1 by 4 will be 0, and thus from second onwards the terms will be cancelled, and what remains? So this term, so 1 by 3 is cancelled with the earlier term. So from the last bracket, this 1 by n will be cancelled with the earlier term in the earlier bracket, and in this way, so only the first and the last will remain, and this is 1 minus 1 upon n plus 1. So for that purpose only we have expressed this an in this form, so as to add the first n terms, and the addition is only 1 minus 1 over n plus 1. So this is what we have obtained is Sn. Now we shall take its limit, and limit of Sn will decide the sequence, the series is convergent or divergent. And what is limit of Sn? Limit n tends to infinity of Sn is equal to limit n tends to infinity of 1 minus 1 over n plus 1, and limit of 1 constant is the same, 1 minus, and limit of the second we have to consider only, and we know that limit of 1 upon n plus 1, as n tends to infinity, the denominator becomes infinite and the limit will tend to 0. So therefore this is 1 minus 0 is equal to 1, and thus limit of Sn is 1. So sequence of partial sum converges to 1, and by definition the series also converges to 1. This convergence of the series depends on convergence of sequence of partial sum, and therefore so this is limit of Sn. So this shows that the series, what is the series original? It is 1 upon n into n plus 1 converges to 1. Or it is a convergent series, and this completes the solution. The second example is of a similar type. We can consider as whether the series summation n takes value 1 to infinity log of 1 plus 1 by n converge or diverge. That we have to decide, and this can be done in the similar way as in earlier example. We have to form Sn and find the limit of Sn. If it is finite, the series is convergent, and if it is infinite, the series will be divergent. So we shall form Sn first, and before Sn we take this as An. Let An be log of 1 plus 1 by n, and we can simplify this as therefore An is equal to log of, we add the terms, take the LCM as n, so it is n plus 1 divided by n, and further we use law of logarithm. So this is log of n plus 1 minus log of n. So this is An we have expressed in the form, and now we write Sn. So what is the Sn? The sum of first n terms. Let Sn is a1 plus a2 plus a3 and so on up to an, and use this expression. So therefore what will be Sn here? Sn will be a1 means put n is equal to 1 in this expression, log 1 plus 1, that is log 2 minus log 1, this is a1, plus put n is equal to 2 to write a2. So these terms are in subtraction, we should write in bracket. So n is 2, this is log 3 minus log 2, and plus next will be log 4 minus log 3, and so on. So what will be the last? As it is. So plus so on. The last is log of n plus 1 minus log of n. So this is Sn. Now as earlier we may observe what will be this sum. See, there are terms with positive and negative sign, and that gets cancelled. So here we may observe log 2 minus log 2 becomes 0, log 3 minus log 3 becomes 0, and so on. So but this term will remain. because it will be cancelled with the earlier bracket, and there is no previous bracket to this term. This is the first term. So log 1 remains, and also in the last expression what will remain? So this see, first term gets cancelled with the next bracket, and second term will be cancelled with the earlier bracket. So this will be cancelled with the earlier bracket, and so this will remain. This will not be cancelled, and this will not be cancelled. You may observe this and verify, and thus Sn becomes, so Sn will be minus log 1, and last remaining is log of n plus 1, or I shall write this is log of n plus 1 minus log 1, but we know that log 1 is 0, and therefore Sn is log of n plus 1. And now we will take the limit n tends to infinity of Sn is equal to limit n tends to infinity of log of n plus 1, and that means as n tends to infinity, n plus 1 tends to infinity, and log of infinity, we know log of infinity is infinity. So while log of infinity is infinity to the base e, since as e to the power infinity is equal to infinity, so therefore log infinity to the base e is again infinity, and thus limit of Sn is infinity means Sn diverges, and this shows that the series also diverges. Sigma original series log 1 plus or given series in this form. So because we have written an for simplifying or adding these terms in this form, and thus the original form of an is this one, log 1 plus 1 by n takes value 1 to infinity, is divergent, diverges to positive infinity. So thus this completes the solution of the second. And one more example we shall consider is, that is third. The series sigma we denote by k notation. It may be denoted by an or ak or say some other am, etc. So it is ak, k takes value 1 to infinity, is convergent. Convergent if and only if given epsilon greater than 0, there exists n belongs to I means n is a positive integer. N belongs to the set of positive integers such that absolute value of this k takes value from m plus 1 to n of ak is less than epsilon for n greater than or equal to n. So this is an important example or problem, or which is also known as Cauchy criteria of convergence. So this is known as Cauchy criteria of convergence, because this is the meaning of this expression is this series, the sequence Sn of partial sum is Cauchy, and then if the sequence of partial sum is Cauchy, then the series is convergent. That is the meaning of this problem. Now what is the statement? This series sigma ak is convergent if and only if this is equivalent or two-way. If series is convergent, then this statement holds, and converse also is true. That means if this condition is satisfied, then the series AK becomes convergent. Now this is easy to prove. We shall consider the sequence of partial sum first. Let Sn solution for this. Let Sn be the sequence of partial sum, or Sn be the partial sum means it will be a1 plus a2 up to an. This is Sn. And now we will see we first consider this. Sigma ak is convergent. Therefore, summation, this series is convergent. What this will imply and implied by? We will write the equivalence statement for this. So this implies and implied by this series sequence Sn is convergent by definition. When we say series is convergent, the sequence of partial sum is convergent. So this implies Sn as n takes value 1 to infinity is convergent. Sequence of partial sum is convergent. And we know this convergent sequence is a Cauchy sequence. In the chapter of sequences, that is important result, or for sequences of real numbers, Cauchy and convergent are equivalent. Convergent sequence is Cauchy sequence and Cauchy sequence is convergent sequence. So this implies and implied by Sn is a Cauchy sequence. And now we use the definition of Cauchy sequence. So this implies and implied by given epsilon greater than 0, there exists n, capital N belongs to I, means natural number capital N, such that absolute difference of nth term and mth term is less than epsilon. Here we shall assume n is greater than m, or if m is interchange, if m is greater than n, we interchange the terms, and the assumption is n is greater than m, and such that n greater than m is, and both are greater than or equal to m. So this is the definition of Cauchy sequence we have studied in the chapter of sequences. Sn is convergent is equivalent to Sn is Cauchy and is equivalent to this definition. Now that this implies and implied by. Now see, the same condition will hold. What is Sn minus Sm? The Sn means the sum of first n terms and Sm is sum of first m terms. So this is Sn, and I shall write the expression a1 plus up to a1 plus up to am, and but m is less than n, so am will appear earlier, and then the next term will be am plus 1 and it will continue up to am. So this much is Sn, a1 plus up to am, and m is less than n, so m will appear here am, and next will be am plus 1 minus what will be Sm. Sm I shall write in another bracket, sum of first m terms a1 plus up to am, and this difference is less than epsilon. This difference is less than epsilon for m n greater than m greater than or equal to m. And thus now you see, observe this difference. First m terms cancels with this first m terms, and what is remaining? The terms am plus 1 up to am will remain. So this implies and implied by am plus 1 plus so on up to am. This part will remain and is less than epsilon for n greater than m greater than or equal to n. And thus this is exactly this notation, summation k takes value m plus 1 to n, and that is less than epsilon. So I shall write here. So that implies and implied by sigma summation k takes value from m plus 1 to n of ak, and that is less than epsilon. Here n greater than m greater than or equal to n. So this is what we wanted to show. Summation k takes value m plus 1. Then next is Kam plus 2 and so on up to An. So that is written in sigma notation. So and that is less than epsilon. Nm greater than or equal to n. So here our assumption is n is greater than m, and thus this proves the result, or this proves this result. Sigma k is convergent. The series is convergent if and only if it satisfies the Cauchy criteria. This is Cauchy criteria because we have used the definition of Cauchy sequence, and thus the series is convergent if this condition is satisfied. Hence the result. So thus in this lecture we have defined convergent series, divergent series, and we have proved two results, theorems, and we have solved some problems relating on this result. The remaining part we will continue next time. Thank you.